Thanks everyone for coming to our presentation today. My name is Arsh Karakia.
My name is Alex.
I'm Sean.
I'm Charles.
I'm Matthew.
And I'm Sapir.
Once again, thank you for coming, and we'll be talking about our project, the RealValue algorithm. Next slide, please. Now, despite the advent of COVID-19, residential sales have grown by nearly 35% compared from January 2020 to January 2021. This provides an incredible chance for homeowners to make a profit in a seller's market. However, price estimation can be a tricky process, knowing what your house is worth, because you might have to commit to realtors, you might have to assess what your house is worth by remodeling, it might involve a lot of paperwork. A lot of tricky things may make you as a homeowner discouraged from pursuing an incredible opportunity. The RealValue algorithm allows you as a homeowner to understand what your home is worth from the comfort of your phone or your computer. Next slide, please.
So for the data set, there were two main data sets that we used. The first was the California data set, and we got this one online off of GitHub. And it was a good starting point to see where the project was heading. So this consisted of images of bedrooms, bathrooms, kitchen, and a frontal view of the house, as well as statistical information regarding the number of bedrooms, number of bathrooms, price, square footage, and zip code. And there were over 500 houses. Later on in the project, we moved on towards the Toronto data set. And since this was expected to have a lower number of houses, it seemed like a good opportunity to use transfer learning, which we'll touch on later in the presentation. And for this one, we constructed the data set ourselves. And we did this by collecting images from the Toronto Regional Real Estate Board. And to stay consistent with the California data set, we retrieved the similar statistical and image information. So the number of bedrooms, bathrooms, price, room dimensions, and zip code. And it turned out to be around 157 houses. Next slide, please.
So I'll be going over our model inputs as well as how we pre-process data. And a cool thing about RealValue is that our neural network is trained on both statistical as well as image data. Statistical inputs for the dense network features include the number of bedrooms, the number of bathrooms, its square feet, zip code, as well as the latitude and longitude. While the image inputs are for the CNN, where we combine images of the bedroom, bathroom, kitchen, and frontal into the result shown here on the slide and feed it into our neural network. One thing worth mentioning is that we carefully limited the amount of features for our inputs so that anyone that has access to the internet can gather the data themselves and put our model to good use. Next slide, please. And we all know how important the pre-processing as well as feature engineering steps are for data science, machine learning. And so for our image data, we perform various randomized augmentations to double the amount of training data that our model can learn from. From this example, you can see some of these augmentations include cropping the image, flipping, rotating the image, as well as altering its brightness and saturation. And as for our statistical data, because it was gathered from GitHub, most of it's relatively clean, but some techniques worth mentioning is that we one-hot encoded the zip code for the California data set, as well as converted the zip code to latitude and longitude for the Toronto data set. Next slide, please.
So I'll go over the network architecture of our project. Due to the nature of our input data, we needed a network that would accept both multi-inputs and mixed data types. Thus, we created a network consisting of both a CNN for input images, as well as a dense network for statistical data. The merged house image was first fed into the CNN, while corresponding numerical data for that house was fed into the dense network. At the end, the results from both branches were concatenated together and then passed through another fully connected layer that performed logistic regression. Finally, a single value is outputted, which is the price of the house. The CNN model that yielded the best results for us was an EfficientNet B0 architecture. Next slide, please. This architecture contained pre-trained weights from ImageNet. We employed a configuration file that controlled the various hyperparameters of a prediction model, as can be seen on the slide. We evaluated our model with a mean absolute percentage error loss function. So for each house sample, we take the ratio between the absolute value of our prediction error and the actual price. This absolute value ratio is summed for every house sample in our data set, and then divided by the total number of houses. The result is presented as a percentage value. For example, for $500,000 house input, if our model had an overall MAP error of 20%, this means that the prediction would fall between $400,000 and $600,000. Next slide, please.
So here's a chronological overview of how we actually created RealValue. In the first step, we compiled the California dataset and applied data augmentation, as Sapir and Charles mentioned. And then in the second step, we trained our model on the California dataset and experimented with different combinations of hyperparameters, models, and architectures. And the best weights for the best performing model, which was the one that Alex mentioned, was then saved. Then in the third step, we compiled our own Toronto real estate data set consisting of images and also numerical data for houses. And in the final step, we applied transfer learning on this Toronto data set after making a bunch of modifications to the model, which Sean will touch on a bit later on. Next slide, please. Now, during the training process, we tried out two different types of models with different encodings for zip codes. The first was using one-hot encodings, and the second method was using latitude and longitude values for zip codes. And we tried both on the California dataset, but only the latitude and longitude model was used for the Toronto dataset. And this was because there were not enough distinct postal codes in the Toronto dataset, so we decided to use latitude and longitude values instead. Next slide, please.
So transfer learning was a key focus of our project, and we use it in two ways. Firstly, we pre-trained on the larger California dataset before training our final model on the Toronto dataset. And then secondly, we used EfficientNet as our CNN model. So for transfer learning, it involves taking your generic network and then separating it into a pre-trained component and a trainable component. For us, we decided to reuse the CNN weights from the California dataset in our final model. And the reason why we did this is we had a simplifying assumption where we assumed that the types of possible images that we could get in both the California dataset and Toronto dataset would be similar. In other words, we expect like the types of houses to be pretty similar in Toronto and California. So we reused the CNN weights. Note that this assumption may not apply to like other geographical areas such as Europe and Asia, where they may have different types of house styles. We retrained the dense network in the final logistic regression output unit because those are dependent on the property statistics and the price, which are very widely between California and Toronto. Some of the benefits of the transfer learning we used was reduced training time. So we could actually train our model on our own personal computers rather than relying on a more powerful setup. We got better performance, and we were also able to use a smaller data set. So this was easier for us when we were compiling the Toronto data set. Next slide, please.
So in terms of results, like Matthew just mentioned, we trained models that considered one-hot encoded zip codes and also normalized latitude and longitude considerations. Initially, it is slightly concerning that we got lower error with our zip code version because we ended up using the latitude and longitude version later for transfer learning. But because the Toronto dataset is much more concentrated and there is less frequency of houses per zip code, the latitude longitude training ends up becoming better. And you'll see that in the next slide. So with zip code training, with one-hot encoded zip codes, we got 17% test error. But with latitude and longitude training, where we normalized the latitude and longitude of every home, and we used transfer learning from the California dataset, we got 14.9% test error. For example, for a house that's worth 400,000, the estimator, in this case our algorithm, would provide estimates between 350 and 450,000, which is quite reliable in our opinion. Altogether, to improve the model, incorporating more data as time goes on and more attributes that are easy to get by a consumer, by a homeowner, would make the model better. Furthermore, this project was a demonstration that transfer learning from bigger datasets to smaller datasets work. Altogether, this project was a proof of concept that incorporating home images and not having that many attributes for a house that allows for consumers to just input information that they know best, proves that the model works, and it can work for any average homeowner. Some of our next steps include stakeholder testing. And as part of that, we like to encourage you as viewers to take a look at our website, realvalue.ca, and I'll be sending a link in the chat right now. So as we have questions and answers, I'd encourage you all to just take a look at the website and try out the software. See if there are some questions that you may have about it. And if you can upload a few images of your own and see if the predictions that the model gives you make sense, then as creators of the model, that provides us with a lot more validation. Thank you for listening.